So how many of you are already NERSC users? Already have an account? Just a few. Okay. So my purpose in today is to both give you an overview of the hands-on, some tips that you're going to need for the hands-on, but I also want to give you a little bit of an overview of NERSC, because even though those of you may not be users right now, but someday you're going to finish up, you're going to go out and become a professor, you may want a way of doing computational science, and NERSC may be the perfect vehicle for you to do that. NERSC is the nation's oldest open or non-classified supercomputing center, established in 1974. We are, I have to remember this all the time, the National Energy Research Scientific Computing Center. It has that name because it began at another laboratory down the street from here with an emphasis on plasma fusion research as a complement to an experiment that was going on there at that time. Today we have completely broadened the mission to cover all of the areas of importance in computational science, including biocomputing. There's an awful lot of that that's been happening recently. And our mission is basically to help you get your computational work done, to accelerate the pace of scientific discovery in your work by providing a combination of supercomputing cycles and data communications and guidance, consulting services to all of the research that is sponsored by the DOE Office of Science, which is the largest sponsor of open scientific research in the country. The fact that we do this leads to all of the principal investigators who use NERSC reporting 1,500 or so publications a year that were based on, at least in part, some resources at NERSC, and many of those publications wind up being chosen as cover articles for some of the journals that you can see here. The workload, as we saw earlier today, is quite broad, lots of users, lots of projects, lots of codes. The thing that I want to emphasize on this slide is that we at NERSC do not decide who gets to use our facility. The DOE does. Some 90% of the cycles at NERSC are allocated by program managers at DOE through a proposal-based process. It happens every year, and starting up in about 1 month from now, we get to allocate about 10% of the cycles that are left. Those 6 offices are shown here. They span basically all of the important areas of computational science. So this effectively is a bureaucratic look at our workload, and you can see the thing that all 6 of these offices have in common is they like to think they have all of NERSC under their control, but you can see they've got it divided up. And if you look at it in what really matters in terms of science, you can see that basically everything is covered here. This is a little bit old. Bioscience has increased quite dramatically with the Joint Genome Institute, which is in Walnut Creek, now having a large allocation at NERSC. There are some important differences between NERSC, which is the high-performance production computing facility, and some of the other facilities that you may have heard about, the so-called leadership facilities at Oak Ridge and Argonne National Laboratory, which each have on the order of a few hundred or so users and on the order of tens or so projects. As I mentioned, almost all of the cycles at NERSC are allocated by DOE, whereas Oak Ridge and Argonne allocate a lot of the cycles on their machines. Basically, if your advisor has a grant of money from the DOE Office of Science, you are guaranteed time at NERSC, which is not necessarily the case at the leadership facilities. You have to have codes that scale to the largest extent possible, and there is in fact no commitment to fund Office of Science research there. Another interesting difference is that we go out on open competitive procurements to acquire our machines, and that leads to a slightly different approach to supercomputing than the leadership facilities who do it through partnerships. As you've already heard, the platforms that we have installed right now are actually a little bit low. We have the Hopper, which is a state-of-the-art Cray machine, and the machine that we'll be using today, a Carver system, which is an InfiniBand-based Nehalem, Intel Nehalem cluster. And You can see some of the statistics there. We also have some test beds. There's a very small GPU test bed called Dirac at NERSC. Now, all of this is part of a very carefully planned out roadmap. The Hopper system and sticks was installed about 1.5 years ago. We, within about a month, will install our new machine called N7 back in our Oakland Scientific Facility. It's a Cray Cascade, one of the very first versions of the latest architecture from Cray. We've also formed a committee now to go out and begin interviewing vendors to put together a request for proposals for our next machine, which we call N8. We hope will be on the order of maybe 20, 50, or maybe as much as 100 petaflop system. The NERSC 7 system coming in, I believe, is on the order of 2 petaflops or so. And as you can see, we're moving to a new building up here in Berkeley within about 2 years called the CRT, and the new machine will go in there. The other thing that I really want to emphasize is that supercomputing, as you probably know, is not just about access to cycles, and it's not just about us providing cycles. We provide also an enormous amount of application software. Some 13 or so million lines of software are compiled and made available for you, including our very good friends at the ACTS who participate and work with us as well. So let me talk about how we're going to actually use these machines here. You're sitting at a machine at your desktop in this room here. Let's say it's called Term. You have to have an SSH client on that machine to access NERSC. It's very important for you to use this uppercase Y option in your SSH command because some of Samir's software requires X windows, and that -Y option will forward X windows for you to the Carver system. This is the letter L. Don't forget that if your user ID on your laptop is not train some number, train 1, I happen to be train 47, then you need to use this option as well. Once you get onto the Carver system, some of you may like to do some customizations. You'll set up the editor the way you like it or whatever. Customizations must go into these files that have .ext on the name of it. You cannot edit .cshrc. You cannot edit .bashrc. It's got to be bashrc.ext and cshrc.ext. And those will be set up for you already in your home directory, and you can edit them as needed. As Samir mentioned, almost all of the important software on the NERSC systems is accessed via something called the module utility. Why we do this, it allows NERSC to make many different installations and versions of those installations available simultaneously for the same software package. You can choose which one you want to use, and it allows you to very easily update your entire environment to choose whichever one you want. The module utility consists of 2 things. It consists of a command, the module command, and the thing that the module command operates on, which we call a module file. And I give you lots of examples of that in the next slide. There are really only 5 module commands that you need to know. Module avail gives you a listing of everything that's available. The output for module avail will be quite large. If you happen to know which software you're looking for, you can use module avail software name, and it will give you all of the versions of that software name that are available. To see which ones you actually have loaded in your environment, use module list. Try it out right now if you're on Carver, and you'll see that there are 2 module files that are loaded by default for you. To load a new one, you have to know the module file name. So it's module load, module file name, and that will change your, yes?
So you don't have this set of slides yet, but we're going to make them up.
This set of slides is available right there.
Oh, good. Thank you.
www.nersc.gov is our NERSC homepage, /users/training, and they're right at the top of the page.
Thank you.
The swap command really shows the power of the module utility. You swap one existing module name for a new one, and it swaps all of the environment variables that might be involved in that. So let's say you had version 1.2 of PGI loaded and you wanted to try 1.3. So it would be module swap PGI/1.2, PGI/1.3, and it changes everything magically. This is actually very useful. It will show you what this command will do without doing it. It shows you which environment variables and other variables are set. And then you can sometimes get some help for what this module actually does for you, is it does FFTs or LU decomposition or whatever. It'll give you a little bit of information there. Okay, now, compiling environments, there's a little too much on this slide for what you guys are going to do here, but I want to make sure you understand two important things. The default environment on Carver is PGI, the Portland Group compilers, and that's what we're going to use. That's what we're assuming for this entire week. The other thing that's completely important here, I believe all the work that we'll be doing this week is MPI, is parallel compiling. As Samir mentioned, the compilers you should use for MPI, Fortran, MPI F90, C, MPI CC, and C++ is MPI upper CC. This, by using this, it will get you all of the include files and all the libraries that you need for the Portland Group compiler. If it turns out you enjoy inflicting pain upon yourself, you can try some of these other compilers. The only reason, I mean, they work just fine, but I don't know that the exercises for this class have been set up to use them. So use them at your own risk in that regard. If you're going to use them with MPI, 2 steps are required. First, you have to swap PGI for the other compiler, and then you have to swap OpenMPI. But I really recommend that you not do that type of thing for this class. This slide, however, is very important. It shows how we're actually going to run here. Is there a pointer? Is this a pointer?
Samir, where is it?
No, just, I think that is a low.
Oh.
Pin pointer right there.
Okay. Anyway, thank you very much. From SC10, isn't that cute? Okay. So here you are sitting in this room, and you're going to use that command that I showed you before, SSH-Y to carver.nersc.gov. That's going to put you on what we call a login node. You can't really do very much on a login node. You can edit your files using whatever editor you like. You can copy files over there. You can compile, but you cannot run the code there. In order to run the code, you need to get over to the compute nodes, and to do that, you must use the batch system. There are 2 ways to use the batch system, what we call the batch way and the interactive way. I think I recommend for this class use the interactive way. It's got pluses and minuses, as you'll see. To use the interactive way, it's this very simple command, Q sub minus I minus V, uppercase. This will go off and think for just a quick moment, and when it comes back, you'll be on a different node, and you can run, therefore, your program. If it's a serial program, just type a.out. If it's an MPI program, and again, I think most of them are here, type MPI run however you would normally run that program. The other way you can do it is to use a batch script called, in this particular case, you can call it whatever you want, batch_script.pbs. I'll show you how to do it in a moment. And then you submit this batch script to the batch system using this command, and in that script will be your MPI run command, and that command will then run on the compute nodes. And again, using MPI run over here, we'll run it on the compute nodes.
Harvey,
Yes.
when you do the interactive, you are going to be placed back into your home
I'm going to get there.
Oh, great.
Momento per piacere. Some notes. Q sub minus I minus V unfortunately has a 30-minute time limit. What that means is you're going to get 30 minutes and then it's going to log you off very unceremoniously in the middle of whatever you are doing, editing, running, looking at a file, whatever. It's going to dump you back onto the login node. And it actually takes about a minute to do that, but there's nothing we can do about that. So you can use this command to see how much time you've got left. qstat minus u, whatever your user ID is, train 1. Okay? As Tony mentioned, when you use this command, regardless of where you were when you typed it, it's going to put you back in your home directory. So somehow you have to navigate back to where you were. And an easy way to do that, if you can remember this, is cd $PBS underscore O underscore work dir. It'll put you back to where you typed the Q sub minus I minus V command. By default, we're going to give you 8 processors to use for your MPI jobs today. If you need more than 8, and I'm not really sure, maybe for Samir's work you might need to, you can append this. This is the letter L, not the number 1. Q sub minus I minus V minus L nodes equals 2, ppn equals 8 will give you a total of 16 processors on 2 different nodes. This also uses the debug queue, and we have the debug queue set up so that each user can only be running 1 debug job at a time. So if you submit a second one, it's just going to sit there until your first one ends, either because it reached the 30-minute limit or because, I forgot to say actually, if you want to finish it before it reaches the time limit, you type exit. Write that down, please. I forgot to put that in here. And again, I've told you all this stuff already. And then finally, this is what a batch script looks like. You can just copy this and paste it into an editor session. You put your own executable in here, your own job name, and that's it. Any questions? I'll be walking around trying to help everyone out. We'll get through this. Samir.